Hello, it's Keith here, and this is lesson 7 of the Photon series of my 68,000 assembly programming tutorials. Today we're looking at the NeoGeo, and this is the last of the Photon series, hopefully. I don't think there's going to be any more, but we're looking at the NeoGeo last, and the NeoGeo is a little bit interesting. Now, this is sort of a joke episode in the sense of I've got this game working on this system, but I really wouldn't recommend this. This is the best way I think is possible on this system, but it's not really viable for this game to be ported to this system, because basically the problem is that the classic NeoGeo, the tile map is all in ROM. Now, the other systems we've used the tile map to define pixels and use those pixels to make the game graphics, because this is a vector-based game, it's a Tron game. So the NeoGeo can't do that, the original NeoGeo, because all of the graphics are ROM. Now, I've worked around that by creating massive banks of sprites that represent every possible pixel on the screen, which we'll go into in just a moment. That said, you could actually do this game more properly on the NeoGeo CD, but for time limitations I don't have any more time to cover more systems, so I'm afraid I don't cover the NeoGeo CD in these tutorials. So as I say, that system could do it better, but we don't have that system available to us. So what I've done is this sort of workaround. I do enjoy pushing the limitations of these systems, and in this case the limitation was that there is no software-based VRAM. There's no VRAM, it's all VROM, so to speak. So I've worked around that, and we've got the game working, but it's terribly low resolution and doesn't look so great. So as I say, I wouldn't really recommend this from the point of view of making a viable game. But if you wanted to make this game on this system, this is, to my knowledge, the only way to do it. So it's a proof of concept, I suppose you could say. You can see the game is working, that it does have now color attributes. Basically, there is only one color. If I can just make it happen. Basically, yeah, there we go. There's only one color in every 2 pixel wide and 4 pixel tall block. The reason for that being is that's the size of each sprite. The sprites are scaled down heavily to fit them on the screen, but we've still got some limitations in there. So as I say, it's far from ideal. The resolution's a bit low, but it does work, and I thought originally I wouldn't be able to get this game running at all on this system. So, you know, it's swings and roundabouts. But anyway, as I say, that's what we're doing. Whether you think it's a good idea or not, I wouldn't disagree that it's a bit of a strange idea. But yep, I got the game working, and so once again, this game has been ported to all of the systems within my 68,000 series, even this one that maybe it doesn't make a whole lot of sense. Now, the way that we've done it is basically to create banks of sprites. We are creating 256 sprites for each color, and these represent every possible combination of pixels within a 2 pixel wide and a 4 pixel tall block. And the reason for that size is because basically scaling down the screen and filling the screen with the limited number of sprites that the NeoGeo can do, that is the most optimal. Now, I should point out the NeoGeo doesn't technically have a tile map. We use sprites and we chain them together to build a tile map. So I'm kind of using those words interchangeably because we're using sprites to affect a tile map. So anyway, so I generated the bank of sprites here. If I just turn the grid down on this so we can see a bit more clearly. So this is all of the pixels being empty, and this is all the pixels being filled. And then you can see as we go down and we go across, we're basically sequentially doing every possible combination of that block being filled. And this is generated by Sprite Editor. There's a special command here in Sprites, generate pixel map, which was configured solely for this task. That's why I've got my own Sprite Editor, so I can do crazy silly things like this. Now what we've done is we've got 256 sprites here that are every possible combination in one color, and then what we've done is we've copied that and we've done it in different colors for the 4 colors, excluding black, that this game requires. So we can do basically the colors, and you can see here we've got the title screen here in the screenshot, but you will see there is color clash, like the tongue here has changed part of the shape of the body here, which should actually be magenta. But to say that's the limitations we've got. Okay. So we've got our sprites here that we've exported into the ROM, and we're going to see those in the game code, and that's how we've got the game working. Now, I'm going to have to cover the gameplay once again. I cover this every time, but it's important you understand some of the rules of the game because we will see them in the code. So if I just start the emulator up again here. Okay, so the first thing is we do have a boost mode. If I press fire, I will move faster, you can see there. And also when we turn, if I turn once and keep holding the button, we don't turn another time until I release and press again. There's a sort of key timeout there. We will see those in the code, so it's important I explain them. let's go over to the source code and let's see it all in there. Okay, so the first thing we've got here is, as always, we've got the color definitions. Despite our rather terrible limitations this time, we do have all 4 colors. So we're defining all 4 colors. So color 1 is color 1, color 2, 2, so on. It's only for systems that don't have 4 colors we have to remap them, but this one we can have them all. Now we're defining the screen size. Now we're defining screen width 20, which sets it to use the low resolution mode. This is really designed for things like the Atari Lynx. And as I say, this is a bit of a satirical episode because it's not really viable. We've basically turned the arcade quality NeoGeo into an Atari Lynx, unfortunately, which is a shame. That's all we can do though. We're then defining the screen size. The screen size is effectively 192 by 124. Now the pixels aren't quite square in this calibration. We can make them square, but the screen does end up smaller. And the reason for that size is we can only have 96 tiles across the screen, 96 sprites, sorry, and each sprite can have up to 31 tiles attached to it, and so that gives us an eventual resolution, being as each of those tiles is 2 pixels wide and 4 pixels tall, of 192 by 124. So that's why we've ended up with that screen size. Okay, we're then defining some user memory for the game variables, as common on every system. We've got our ROM header here, more nasty ROM stuff here. We finally get down to the actual start of our game here at this point. So we're starting off by defining our color palette for our game graphics, setting up the sprites and the background, the fixed layer, and then clearing the game variables. And then what we're doing is we are defining the sprites and we're putting them on screen. Now, like most systems, we need a tile map visible on the screen, and we're going to alter the tiles within that tile map to show pixels on the screen. So what we're doing in this case is we're creating sprites, chaining them together, and that's creating our tile map out of sprites. Because as I said before, the fixed layer is sort of a tile map, but we're not using that in this case, we're using the sprites. We couldn't really do this with the fixed layer so well. So what we're doing here is we are defining our settings here. We're setting our scale here. We're scaling down the sprites. The sprites are 16 by 16 pixels, but we're scaling them down very small, and we're kind of squashing them as well. So we're giving it rather a weird scale to make it work. So we are scaling them down there. That's the scale for that. And then we're defining the width here and the height of the number of tiles to add. We're adding 30 tiles to each sprite, so 31 in total. And then we are defining the scale. We're defining this to be a looping option here, which effectively makes, that's how we get the most tiles on the screen, so to speak. So it will repeat if we scale it down too small. Okay, so we're defining our positioning here of the start of the tile map, and then what we're doing here is we are basically adding tiles to each of the sprites. That makes it that's the vertical part, and we're doing that to create each sprite, and then we're repeating for the next sprite here. So this is the settings. This is basically a copy of the tile map example I did in the past, but we're scaling it down this time so that we get the sprites filling the entire screen the best we can. Okay, so that's defined what is now our tile map. We now don't need to reset that up again. All we need to do now is tweak one of the sprites that's in the position of the pixel we want to draw on the screen. What we're doing next is we're clearing the screen and showing the main menu, and this is the title screen, and once the player presses fire, the game will start, and that's this loop here. We're kicking the watchdog here. That's always very important to stop the game crashing. And then what we're doing here is we're updating the game tick. Now the boost mode will update the player's movement every tick, but when boost mode is off, we only update the player's movement every other tick. That's how we slow the game down. So that's what that's doing. We then got a delay here, and the delay is different if boost mode is on. And the reason for that is boost mode has to update the counter in the corner, and it takes a little bit of time. So it's to compensate for that. We're then checking the key buffer here. We are reading in the controls, and we are updating the key buffer if any directions are pressed. If a direction is not pressed, we're clearing the key timeout, and that's what we're using to check if the player has released the keys, because we don't process left being held down, because if we did, the player would circle and crash into themselves, or at least that's what I was doing. Maybe I've just got poor reactions, quite possibly. Anyway, so that's what we're doing there. We're repeating until the delay is finished, and then we're checking the key timeout, and if it's not 0, then we're skipping over the directions. We're then turning boost off, which we do by moving a 1 into the boost variable here. We're then loading the player's direction and the acceleration into A3 and A6. Now, these are used by the turning routine set player direction. It basically alters these. The player's direction is one of 4, north, south, east, west. It rotates clockwise or counterclockwise, and the way we do that is we just increment or decrement that player direction. We then run set player direction, which updates the accelerations, and the accelerations are added to the current player position. And so it's setting those correctly depending on the movement direction. If the player has moved left or right, we set the key timeout. Finally, we check the fire. If fire is pressed, then we check the boost power, and if there is boost power, we clear the boost variable, which turns boost on. That's how we do that. The actual boosting and the moving and all that kind of thing is done by the handle player routine, which is the multi-platform code. We want as much code as possible in the multi-platform section. Handle CPU does the CPU, and then we just repeat until the game has finished. Basically, that's the entire game loop. Very small, which is what we want. Unfortunately, the new game I'm writing, the Suck Hunt game, is not small at all. There's lots of complex code there. Never mind, this one's nice and simple though. Anyway, so that's the game logic. We're now really getting on to the sort of meat of this tutorial, which is the PSET and the point routines, and they're very similar. So basically there are 2 stages to this. First, we need to work out from an XY pixel coordinate and a color number the tile of the sprite that we need to alter, and we're then going to read in the current tile number, and we're going to OR in the new tile number of the pixel we want to set, and that will effectively select the new tile number. We then have to select which bank of tiles, because there's 256 tiles per color depending on the color, and so that's what we're going to be doing here. Now, the X and Y coordinates for this pixel are in D1 and D4, and the color is in D2, and so we're going to see those used when it comes to calculating the tile number and then the pixel. So first we're going to calculate the tile number. Now, there's 2 horizontal pixels per sprite because of the scaling, and as I say, it's a rather odd layout, but that's what we've done here. You can see here this is one sprite and this is another sprite, and you can see this is 1 pixel set here, and it's moving up, so to speak. So basically we've got 2 horizontal pixels per tile and 4 vertical pixels per tile, and so because of that we're shifting to the right by 1 bit the X position, which is basically ignoring the bottom bit of the X coordinate, and we're shifting to the right 2 bits the Y position, which is effectively ignoring 2 bits because there's 4 vertical pixels per sprite, and so that is now selecting the offsets for the sprite. We're then multiplying this newly calculated X position by 64 and multiplying this new Y position by 2. Now the reason for that is there's 2 bytes per tile definition within the sprites, and there are 32 tiles defined between each new sprite, which is a vertical line. So the X position is being multiplied by 32 by 2, which is 64. The Y position is being multiplied by 2, and then these are being added, and that's being selected as the VRAM address we're reading from. We're then reading in from that, and that is now giving us the current tile number of the tile that has the pixel we want to change in it. Now, this is a little bit confusing, please bear with me. Okay, so we've now selected the correct sprite that we need, the correct tile of the sprite we want to change, and what we need to do now is work out the new pixel value that we need to OR in to set the extra pixel within that sprite so that it is visible on the screen. So now what we're doing is we're taking the bottom 2 bits of the Y position, and we are now looking those up in a pixel map, and you can see that here, and this is the coordinates of each of the pixels according to the Y pixel that we want to set, and this is of course relating to the order that they're drawn in here. If these were in the opposite order, we'd need to change that the opposite way around and things like that. Okay, so we're using that pixel map here. That's now got the correct Y offset that we need to add in, and then we are checking the bottom bit of the X coordinate, and if the bottom bit of the X coordinate is 1, then we need to skip over the next line. And what we're doing here is we're effectively shifting the value we read in here to the left 4 times, and that is effectively achieving an X offset, because if you look at this map here, we've got all of the right pixels first and then all of the left pixels second. So if we're doing that left pixel, we effectively need to multiply by 16 here, and that's what we're doing here. Okay, we've now got the offset for the pixel we need to set. What we're doing next is we're calculating the color. Now, I don't think I actually defined 16 colors here, but we're just treating it as 16 colors anyway. We're then checking that if we are not writing a black pixel here, clearing the pixel effectively, then what we need to do is we need to strip the current color number. And the way we're doing that, each set of sprites is 256 sprites. You can see this is 256 sprites here. So we're keeping the bottom 2 byte here. We are, however, removing these bits here, and the reason for that is effectively the bank, which represents the color. So we're doing that there. We're then calculating our new color number. We're shifting it into the correct position, and we're ORing the new color bank into this position here. And that's going to effectively set the color for the sprite that we read in. We read in the current sprite from VRAM here. We're now setting the new color for that here. We're then ORing in the newly calculated pixel that we calculated with all of this here. So we've calculated the new pixel we want to set, we're ORing that in, effectively setting that pixel, and we're writing the new tile number back to the screen, and that is going to update the tile number to show the tile map with the extra pixel set in the new color. Yeah, I know that's a bit confusing, but that's what we've done. Now in this case here, we are wanting to clear the pixel, so what we're doing here is we are masking the calculated pixel, flipping the bits, and using that as an AND mask, which will effectively remove that pixel if it was previously set from the byte that was read in from the screen, and we're writing that back to the screen here. So that's how we're doing it. I know it's a bit crazy, and as I said before, this is kind of, if you really needed to do this, this is the only way I think you can do it on the NeoGeo. As I say, NeoGeo CD would have other options because it uses VRAM for its tiles, but its sprite definitions, but this one does not. The point command is basically the same. We're calculating the same position as before, but this time we're using it as an AND mask, and we're checking to see if that pixel is 0 or not, and that's all this game needs. The game just checks if a pixel is black or not black. The pixels that have been set will kill us and the rest won't, so that's how we're doing it here. And then we've got finally a clear screen routine here. This is much easier. All we need to do is set all of the tiles to 0. That's what we're doing here, just zeroing all the tiles, which will effectively clear the screen. So that's it. Now the rest of the code here, we've got lots of other code, of course. We've got the joystick reading routines palette, so all of the screen initialization and the ROM header, but I'm not going to cover that here. I've covered that before in the Simple series and also to some extent in YQuest, so if you need to know how that kind of thing works, please take a look at those because I've covered it before and I don't really want to cover it again. Anyway, that's all we're going to be covering today. As I say, I know this is a bit of a weird one because it's a kind of silly example, but I did have some fun. I've had a sense of satisfaction getting the game to work at all on this system because I previously thought it was impossible. So I had some fun with it, even if it's a bit odd. Anyway, if you like what you've seen today, please hit like and subscribe, because if you like the videos, YouTube recommends them to more people. And if you subscribe, it convinces me to spend my evenings doing crazy things like this, because it does take quite a lot of time. We're going to be coming back, I'm sure, at some point to the NeoGeo. I've just written my new Suck Hunt game, which is a sort of Duck Hunt Operation Wolf parody in 3D, in stereoscopic 3D, and I'm hoping to port that to the 6502 and later the 68000, so you'll probably see that turn up on the NeoGeo at some point. So if you subscribe, you'll see when that turns up. Anyway, I hope you've enjoyed this video today. Thanks for watching. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.